Okay, we're about to start. I think we're almost about a few seconds to the starting time. Good morning once again to everyone, to the tutors and to the participants for joining us today in the week 4 of the BRICS Idea Data Analytics program. Today we'll be talking about um, astronomical data sources. I think over the last 3 weeks, we've been going through Python, how to write Python code, how to use it to perform data analysis, how to clean data, how to perform visualization, how to also do statistical analysis to generate insights from data. This week, we'll be looking at the astronomical data sources, different types of data sources in astronomy, and how to manipulate such data with Python. We're also going to look at some of the basics concepts of astronomy here with regards to maybe how to deal with astronomy data, the units, coordinates, building tables with tools like Astropy, how to also query data from an astronomy data source. So joining us this morning is Alexei. Alexei will be taking us through the introductory part of Astropy, how to manipulate, tell us what Astropy is and how it differs with NumPy and maybe SciPy and the different useful cases for it. And then after that, Priya and Najam will take us through how to do some query as well as how to perform query images from with Python. So Alexei, over to you.
Thanks, Daniel. I hope sound from me is okay.
Yeah, the sound is clear. We can hear you.
Okay. Today we will talk. My name is Alexey Dichenko. I am from Ural Federal University, and today we will talk about Astropy. So let's start. Astropy is a core Python package created specifically for astronomy and created by astronomers. It's built by community and for astronomy community. And today, Astropy has become de facto standard for Python-based astronomical computing and widely adopted by different scientific groups. So we can assume that Astropy is basics of most astronomical Python workflows and pipelines. So Astropy gives us tools for everything from units and constants to coordinate system, data tables, time and calendar systems, feeds, files, maybe even cosmology calculations. For me, it's not common, but maybe you will use. I will be happy. And even image visualization tools connected to Matplotlib. So, why we use Astropy in our work and why we should use? Because it helps us to do science correctly. Astropy helps you avoid mistakes and save your time. Units are automatically tracked, constants are precise, and calculations become transparent. Usually this helps to reduce human error and makes our work reproducible. So Astropy understands units like parsecs, light years, or kilometers per second, and automatically keeps them consistent. Instead of writing tools ourselves, we rely on a shared, well-tested code base developed by professionals. Also, that means your code becomes easier to read, safe to run, and better for publication. Also, many other astronomy libraries already depend on Astropy, and I think it's essential to use Astropy in your work because if you have a knowledge about Astropy basics, I think you can use a wide range of other libraries for astronomy in Python. I can tell a funny story about me from when I first started using Astropy. It was 2.0 early on in my career. Back then, I didn't understand and even didn't like Astropy basics like units and coordinates. As a result, I wasted a lot of time working uh, with them in an old-fashioned way. For example, I used my own code in C++, and actually that was terrible. So don't be like me. You need to start learning basics of Astropy right now. And I hope it will save a lot of your time and make you much more effective. Yes, in modern life, you need to be fast and effective. So Astropy, I hope, provide this to you. But actually, Astropy whole ecosystem, Astropy is more than just one package. The, there is a core library with basic features, like I mentioned before. It helps us with units, coordinates, table, time, cosmology, and so on. Then there are coordinate packages like Astroquery, phototils, specutils, CCD, proc, regions, and other, which follow the same standards and integrate tightly with Astropy. And finally, there are affiliated packages with community developed tools. That means Astropy's quality. They have Astropy's quality and capability standards. But coordinated packages are developed in close collaboration with Astropy projects. Sometimes people from Astropy project also work in coordinated projects. So this structure makes Astropy, I think, both powerful and flexible. We have core packages and side packages, coordinated and affiliated. So we can use some specialized packages with Astropy flexibility. But today we will talk mostly about core packages like Astropy units. Its subpackage brings meaning to numbers. In astronomy, we constantly switch between, for example, parsecs, light years, kilometers per second, and sometimes flux units like, I think, Jansky. With Astropy units, we can attach units directly to numbers and do unit AVMS. Library will warn us if we try to combine incompatible things. Alongside that, we have Astropy constants, a collection of physical and astronomical constants, like I think speed of light, Planck's constant, solar mass, and so on. Of course, all with the right units included. I think this gives us clarity and safety in our equation and in our calculation when we use Astropy units. Of course, astronomy without coordinates, not astronomy. Once we understand units, we move to coordinates subpackage. So coordinates subpackage. This part lets us represent positions of stars and galaxies in the sky using common systems like right ascension and declination, galactic coordinates, and so on. It's very flexible. We can easily convert between systems, apply some motions, proper motions. I remember when I first time did transform code between right ascension and declination in galactic coordinates with pi coords, I guess, and this was terrible. Now it's you can spend some seconds to just transform between every coordinate system I know. And of course, it's fully integrated with units and essential for sky mapping, planning your observations, and work with catalogs. Moving next. Okay. Astropy constants. The package provides physical and astronomical constants with units. You can see a screenshot from Astropy website with table where you can find every constant you need in your calculation, I guess. And all constants are approved by International Astronomical Unit. And of course, unit safe. Astropy tables. Astropy table module works like pandas, but it's built for astronomy. We can define tables with columns that include units, metadata, and even masks for missing data. It's perfect for organizing catalogs, observation results, output of your models, and of course for Astroquery query results. Tables work smoothly with other Astropy tools. We can easily read and write them in many formats, including feeds files, virtual observatory table. By the way, if you prefer pandas, don't worry. You can convert back. You can convert to pandas and from pandas. Okay, why we learn units coordinates tables first? Because they are essential building blocks for working with astronomical data. They are required by more advanced tools like I already said Astroquery, feeds handling, and so on. So let's watch some hands-on practice about unit coordinates, constants, and tables. Okay, I prepared for you some interesting notebooks. And of course, I start with a small introduction to Astropy library. We already discussed about it. So let's see what we have, such code we have. I use Jupyter notebooks, but I think Daniel did a great job, and you can use it in Google Colab without any problems. So in this cell, you can see how to make not just Python scars, but quantities. Quantities, it's number with unit. Key unit, it's kilometer and kilometer per second. Firstly, of course, we input Astropy units module by this command. Of course, I can stop. Okay. So let's start. And here we can see the type of our Astropy quantity. It's class, it's object of class. Our class is Astropy units quantity quantity. So if you print your distance, it will be already with units and velocity, of course, because we define it here, distance and velocity, and by multiplying on unit, we have quantity. You can use, okay, string formats, but what if you want to know just unit of your value, of your variable? Okay, we can print distance, unit, kilometers. We can have access to value, okay, so 1000 kilometers. And we can show, I can show you type of value that quantity store. Of course, it's numpy float 64. So quantity it's unit plus value. I think it's easy to remember and it's easy to use. Full list of Astropy units you can find by this link or in table I provided here. It's pretty useful even for me because sometimes I forget what I need and how to use it in code, in your code. So move on. Another way to define your quantity, use such code. Let's define some distance in parsecs. Okay. Let's check class. It's still Astropy quantity. But maybe we want speed of light to show you, to see speed of light. So we can define in such way 1 light year per year. So it's your speed of light. But what about converting to different units? It's very easy to do. Just use such structure and you will have speed of light in kilometers per second or any other units. I think it's magic. You can find here any notes about how to do it, but let's go next. Okay. We find out how to convert to different units. Now let's have some fun. Okay. It's obvious, but not so interesting. Okay. 16 light years. You can convert to astronomical units, solar radius, kilometers, millimeters, even picometers. Don't do that. All prefixes list you can find in Astropy docs. Let me show you. So just scroll. So yes, every prefixes you need in that table. So I hope you will use it. But what about some standards like C or CGS? Of course, you can convert to it very easily by such code. Maybe you need some value in your favorite units. Maybe you need speed of light in millimeters per nanoseconds. Why not? You can do it very fast and very easy. Now let's talk about constants. Okay, it's still very easy to use. Table of almost all constants you can find in these notebooks. We can split it to physical constants and astronomy constants. Okay, now you know that you don't need to type such numbers. You can use it without any possible errors. Such code we use to import our, for example, speed of light and show it in, of course, C system in meters per seconds. So another way to import, to do it like that, for example, Boltzmann constant, and we can show it like this. Okay, but also we can convert constants as other quantities. So if you need speed of light in CGS system, okay, why not? Very easy. If you want some beautiful to display some beautiful numbers, you can use IPython display with math and display, and I think it's beautiful. But I guess it's work only in Jupyter notebooks. I don't remember. Okay. You have units, you have constants. What we will do? Of course, some astronomical calculations. For example, Stefan Boltzmann law, we will calculate some luminosity of, for example, exoplanet. So here we define exoplanet radius. Of course, in Astropy quantities, we have unit, we have number, so on with the temperature. So we have a radius of exoplanet and its effective temperature. So let's calculate luminosity and okay, let's show the result. Not very easy to use and not really human readable number, but we can show it like as a fraction of solar luminosity. Luminosity we divide by sun, luminosity of our sun, and we need to decompose. We use decompose a function this operation in this case divides a computed luminosity in watts by solar luminosity constant, and our result is dimensionless quantity because both values have the same physical unit. So be careful, because in other case decompose will work in another way. Usually we can use decompose to simplify our quantity by expressing its units in terms of base C units. It does not remove units because it writes them in most basic form. And it's really different from two method, which converts a specified target unit, decompose converts to basic unit. Okay, move on. And let's see. So if we have such units, decompose make a possible list of units which you can use inside this quantity. And of course, Astropy units can easily work with NumPy arrays. Okay, we have time to watch what's happening here. Okay, maybe we want to calculate luminosity not for only one star, but for stars with different temperature, but with van radius. For example, radius of our sun, again, we make a temperature array by, of course, usual NumPy function. Again, luminosity, but we will calculate not just one number. We will calculate whole array of our luminosities. So, and again, let's convert to more human readable units. Of course, if you use 2, it convert all array elements and show 10 elements for you here. And you can use actually a lot of NumPy functions with Astropy units. And I think it's very useful too for you. Okay. Another one useful thing. You can use quantities in Matplotlib. We just need to import from Astropy visualization quantities of support. And as you can see, I did nothing with axis, just PLT plot, and we have our units on our axis automatically. I think that's great for fast data analysis work. Very useful. Please use. Okay. Here, a small summary about units, quantities, and constants. Of course, it's very short, brief. It was very short and brief. You can find additional features of Astropy units by these links. I strongly recommend you to learn about equivalence, maybe custom units, and if you need some beautiful format, unit formatting. Okay. And some not very hard, but I think it's very easy task for you if you want to use Astropy units. So, next one, Astropy coordinates. When we have understanding of Astropy units, we and how to represent our physical quantities with meaningful units, we can move to central topic of astronomical computing, celestial coordinate system. Okay. This model essential for tasks like define sky positions, proper motions, and radial velocities. I already mentioned it in my presentation. So let's go to example. Of course, we import Astropy units. We import Astropy coordinates and import sky coord class. And of course, we can't live without NumPy here. So let's see. Coord, we create object of class sky coord of object sky coord object. So we use right ascension in such way. This is our number and our unit. Great. The same for declination. If you want, we can create frame ICRS, but if I remember right, ICRS frame used for as the default. So let's print our coordinates. But what thing it is? Of course, it's object of sky coord class. Great. So, but sometimes it's maybe not very easy to use such coordinates. Of course, Astropy coordinates can eat any coordinate system. So keep your fingers away from the input. It can eat almost everything in such way. We just define units. Even without units, Astropy will parse with string, hours, minutes, seconds, so on, but with degrees for declination, and so on. Sky coord with such string, define unit, hour angle, and degrees. Maybe in such way. And let's check. Yes, the same numbers. We did not any errors. Great. But how we can access to our coordinates? Of course, you can use it's like class. So coord r right ascension, coord declination. It will show right ascension in string format and declination again in string format. And we can see class. Okay, it's another class. It's about Astropy angles. Be careful. Okay, let's go next. But we don't want strange Astropy angle class, maybe. We want our NumPy numbers. Okay, coord, right ascension, hour, coord, declination, degree. And you have your favorite NumPy float 64. I hope you're happy. But I strongly recommend to use Astropy units to handle all your coordinates because it's much more easier and maybe you will not make a lot of mistakes. So if we print our code, we can do it in different types, not like this one, but with your hours, minutes, and seconds, of course, and so on for declination, but in degrees, minutes, and seconds, of course. Move next. Or maybe you need radians. Of course, you can get it. Fine. Maybe you want some beautiful print. Astropy will say, yes, of course. Degrees, minutes, seconds. Okay. Hours, minutes, seconds. Of course, why not? Move next. How to transform to different sky systems. Very easy. Dot galactic, and you have galactic coordinates. Wow. I think it's great. So very easy. As I mentioned before, when I did it first time, it was very hard for me. And it was a lot of code. Yes, this make me happy. So maybe you need request. You need to know coordinates just by name of your object. Very easy. We can do request to our favorite Simbad system in just very simple way. And okay, we have a coordinates, such easy, and we can use it next. So what's about arrays? Of course, we can use our coordinates as arrays. So we have two NumPy arrays with right ascension, with declination. Let's make our cluster names. For example, this and array with our distances in kiloparsecs. Okay, let's define our sky cohort class again, but in this case it's array. Same way, right ascension, here our array of right ascensions, and here array of our declinations. But what we see here, distance, array of distance. Okay, now we can print our cluster cohorts, and we will see array, actually array of coordinates, but they have units and properly store. Okay. If you want some more effective examples, we can use some function from Astropy cohorts. For example, we can calculate distance between our objects in 3D or just angle separation. Let's see. For example, let's calculate distance between our first cluster and last cluster. Why not? Okay, our 3D distance between NGC 104 and NGC 7078 11 kiloparsecs. Oh, pretty long distance. But our angular separation on our sky 89 degrees. Okay, what about angles? Of course, sometimes we need just angles, not sky chords, but angles. For, I guess, flexible creation from degrees, radians, hours, and so on. Of course, you can easily manipulate your angles. And again, Astropy developers thinking about us, and you can use any form as you need. You can see different forms here. Of course, same operations for angles as for sky chords you can do. Some difference, why not? So, by end of this lesson, we know that we can use Astropy coordinates with Astropy units, and that can make us happy because it's very easy, as you can see, as I hope you can see by this example. The same way, additional topics for you to learn, maybe more about coordinate systems and frame transformations. It's not very complicated. Okay, and maybe proper motions and radial velocities you can find here. Okay, our last topic for today with me, Astropy tables. Another one, package. We already know about it. So, it's very easy to use. Let's define our table. Not just table, but quantity table. As I mentioned before, Astropy tables can use units and, of course, Astropy coordinates. Okay, import numpy, Astropy units, and Astropy table, but qtable. And we create our table by numpy arrays, of course. Our array with star names, distances, apparent max, magnitude, absolute max, temperatures, radius, and spectral types. So, creation of our table, very easy. Just names of your arrays and names of your columns. And some meta information if you want. Not necessary to use it. If we will show our table just in Jupyter cell, we will see it in such form. Pretty easy to understand, I guess. So, but if you will print it by print, okay, I didn't. Okay, I need to start it, sorry. Okay, you will see table in such way. You can easily to copy and move on. Very useful. If you want to specific number format for your table, it's very easy and very fast. Just info format, your format, and let's see. Temperature here and temperature here. With 0, without 0. Very useful, I think. Another very useful thing about table info command. So you will see name of your columns, the data type, units, and class. As you can see, we used quantity. So unit of quantity is light years, but class we use is quantity. Be careful. Or if you need just start table columns, you can make command call names, and you will see just your call names. Very useful too. Maybe you need to some meta data about your table. Very easy. Why not? So let's check our type of our column. Okay, it's still quantity. Great. So how to access to our table? Just our one right here, or we can use only zero row. Why not? Maybe you need third zero. Oh, yes. Yep, it works. Maybe you need zero row. As you can see, if we change it here and here, it will be the same. But still, be careful. Okay, but if you will use your command value, it will be already numpy array. Again, be careful in what you are doing. So, knowledge about quantity and units still useful with tables. Okay, you can use it sometimes as numpy arrays. So, zero row to two row, second row. Yep, it works. Maybe you need some columns only. Why not? Temperature and distance. You will see only them. Again, if you can not use print, but let's show you. You can. If you use Jupyter, you can see this one. Okay, and still you can define unit of your column. That's great. So what we can do? We can add, for example, some new column. Okay, our favorite luminosities. Why not? Calculate our luminosity, convert to luminosity of sun, and just add to your table. Here. Great. Okay. By this short brief, now we understand how to use tables, and it's okay to you successful use of feeds files and Astroquery. For example, if you use Astroquery, it will, okay, it's not my topics, but it will output a table. Actually, it will output a list of tables, but if it's one table, as you can see, it's still Astropy table. That's why I think you really need to understand, use, and learn about Astropy units, Astropy tables, and actually whole Astropy. Okay, I think that's all. I will be happy to answer your question in Slack about maybe you have a maybe advanced question about how to use Astropy, Astroquery, Astropy feeds handling, and so on. So, Priya, I think I give
Yes.
floor to you.
Yeah.
Yeah, okay. Before you proceeds, thanks, Alexei. So guys, if you have any questions, just put it in the chat and put it on Slack, and then Alexei will respond to them. Priya, over to you.
Yeah. Thank you. Yeah. Alexei, could you unshare? Yeah.
Yes,
Okay.
yes, of course.
Yeah. Thank you. Yeah. So after that interesting lecture by Alexei, I would like to do a little bit about basically telling you about what is exactly astronomy data with which we deal, right? And so the data which you're going to handle with Astropy is basically digital data, right? And typically data which you'll find in the archives could be either in-depth study of individual objects or survey data. So that means telescopes basically behave in observatory mode or survey mode. And based on that, you may actually want to study the data. So typically images of typical types, for example, images could be, data could be images, it could be catalogs, spectra, time series, and polarization. So let's look at what are data images. So basically astronomy images are 2D arrays, okay? So you typically have this 2D array with a count on each value, okay? Which basically describes the brightness at a certain pixel, okay? This can be typically in astronomy, you could have either a point source, which is a star, or you could have an extended source, for example, a galaxy. Now, in astronomy, we use what are called CCDs or charge coupled devices. These were basically invented in 1974, okay, by Boyle and Smith, but first time implemented for the Hubble Space Telescope when it was realized that we need to have a very sensitive digital detector, okay. Now, what does a CCD do? It's made up of what are called picture elements or pixels, which you can see over here. And each picture element, like I said, it's you all would be aware of photoelectric effect. That means when photons fall on this on a metal, or it could be even semiconductors in this case, you will have electrons being emitted. That means you have a charge. So all we need to do is we need to measure the charge that is collected on the pixel or the picture element. Now, in astronomy, what is that? In astronomy, what we do is we take images of this kind. For example, we put a filter, right? And then we look at the image of the object that we get with a certain filter. Now, you have digital cameras even on your phones as well as your laptops and various other devices. In these things, what is done is actually you have a combination of filters. In the sense, you have a red filter which looks at long wavelengths, a blue filter which looks at short wavelengths, and you have a green filter which looks at in between. So typically, if this is your CCD, right, or your digital camera made up of pixel elements, you have 50% or half the pixels which are basically green, 1/4 which are red, and 1/4 are blue, right? So what you do is a combination of all this gives you a colored image. Okay. In astronomy, we don't do this. Like I said, we do a single filter at a time and we get images with single filters. Okay. So what we typically do is, for example, you can look at this image on the left. This is basically an image which is taken with a 2-meter telescope, okay, with a certain, and this one is a Hubble image of the same this thing. So what we do is we basically use filters in succession, okay. You do a short, long, and medium filter, right? And then they are combined together, which to give you what is called an RGB image, a colored image like the one over here. But often in astronomy, we also use artificial colors, okay? Now, astronomy images are in a format called the FITS format. So if you heard even Alexei spoke to you, and the next session will be about FITS images, because you are aware of, for example, BMP, PNG. These are the typical formats in which we actually have images, right? But in astronomy, we have a special format which is called the FITS format, or the Flexible Image Transport System. Now, in a FITS format, you could have 2D images, you could even have tables, you even have in a header file. That means a header file basically has metadata or information about the image. Where was the image taken? What is the object? What is the exposure time? What is the filter? Which is the telescope? what was the time of observation, right? So this is the header information, which is also sitting with the FITS file. So in the next session, you will actually see that when you're looking at FITS files, how do you actually read header information? What I mentioned earlier is this is your image bit matrix, and you basically have numbers for each point, which are giving you the brightness of that point, of that region of the image. Goes to mute. Okay. So the brightness also can be adjusted in different ways. So we have a count for each value. This one is an image which is shown to you directly with the count, right? Now, which has a scaling, right? It goes like depending upon the display you have. Supposing it's a 16-bit one, you'll have 2 to the power 16, 65536. So it's from 0 to 65536 is the range in which the you could have the counts, right? Sometimes what is good is you can actually scale the counts. You could have what is called a linear scaling, which is shown over here. Or for example, you could even have a square scaling. That means you square the value of every pixel. Okay. In that way, what happens is you, like in this last one, the range instead of 0.265536, instead now here the range is been adjusted to 4572 to 6002. Therefore, what happens, you can see that the image gets better enhanced depending upon the values or the counts which you have the pixel. So you accordingly adjust the range which you have for the image to display the brightness to enhance the image in a better way, right? So here, for example, is an image of a certain cluster which is called NGC 281. And this image which you are seeing is actually a combination of images. It's called the Pac-Man Nebula. This is what it looks like in optical. If you look in Spitzer, it gives you an image something like this. Okay, this is of the same 281. If you look at it in X-ray by Chandra, you'll get an image which looks like this. So the final image which you're seeing over here is a combination of the Spitzer image, which you see is the redder image, because it is at longer wavelengths, it's infrared wavelengths, and the purple image, which is basically the Chandra image, which is in X-ray, therefore it's purple in color because it's shorter wavelengths. So this is how often if you see an image like this is not a real image. This is artificial colors which have been added on to enhance the image and show features, okay? Like for example, these dust pillars, etc. They show out very nicely in this image. So then images are actually enhanced. So what we actually do in astronomy is a lot of image processing. That means if you have an image, you may enhance it in different ways, or you may do various things on it. What we need to remember is that because the image is like a matrix, so whatever mathematical functions you can do for matrices, for example, you can add images, you can subtract images, right? All those kind of image processing arithmetic functions can actually be done for images, and they are required to be done. For example, if you're processing CCD data or you're doing background subtraction, you may need to want to subtract or add images, right? So this is often done, and it would be done, for example, with Astropy. There's a CCD proc package which will actually handle your CCD data and do image processing, right? Your data could also be in the form of a spectrum. A spectrum is intensity versus wavelength, and therefore you're getting the energy distribution amongst different wavelengths. A spectrum is like a fingerprint of the object you are looking at, because you are aware that supposing this is your continuous spectrum, you will have certain wavelengths at which you may have absorption or emission. In this case, you are looking at absorption. So you can see that the light is getting absorbed by the source at particular wavelengths. If you identify what is the wavelength at which this is happening, you can actually get a lot of characteristics about the object you are observing. Most importantly, for example, if you get a line, right, and you identify, for example, this is hydrogen, right? Hydrogen beta line comes at 6530 angstroms. So then you can say that, okay, this object basically has hydrogen on it, right? So you get the chemical composition. Along with that, for example, if you're looking at galaxies, you will have a redshift. We know about the expansion of the universe. So you will have a redshift, right? So you can actually use, what is a redshift? Is the shift in the wavelength, right? So your delta lambda by lambda is equal to V by C. So therefore you can actually use that. Your redshift will actually be an estimator of the velocity or even the distance of the galaxy, for example, because you've measured the redshift. You could also use the spectral line to actually do what is called thermal broadening to see the temperature of the source and many more other important parameters about the object, which you can get from the spectra. Now, often in today's times, what is done is that you actually have data like a data cube. Okay, this is like a slice of bread. You actually have images in different wavelengths. Okay, so this is the images in blue wavelengths, in green wavelengths, in red wavelengths. So what they've done is that they are stacked together because all these images have the same dimensions. You're looking at the same object, right, at the same dimensions, but only in different wavelengths. So think of it like a loaf of bread where you actually have images in different wavelengths. If I were to take a cut across this, then I will basically get a spectrum because I will see the difference in brightness across various wavelengths. If I take a cut like this, I'm basically going to see the image of the source in a particular wavelength, whichever one I'm interested in doing, right? So these are called, this is three-dimensional data or data cubes, where you can actually have all this information about the source. Data can be also in the form of catalogs. Yeah, there could be catalog data. For example, you have, this is a star cluster catalog. You have the cluster, you have the right ascension, declination, galactic longitude, galactic latitude, proper motion in RA, proper motion index. So you could have data in the form of a catalog, okay, which is a table. So instead of using Excel, which you could use, we actually have a virtual observatory tool called TopCat, which is very effective in using catalog data. Or you can use Astropy because your data can be imported as a pandas data frame and then be used by Astropy. And you can do all your operations with your catalog data. Data can be also in the form of time series data because if you have a variable source, the brightness of the source is changing with time, and you may plot it as a time series, right? So it's the brightness on the y-axis versus time on the x-axis. So like I mentioned earlier, often what is used to display images, there's a software called DS9, Deep Space 9, which is used to display FITS images. To look at catalogs, you could use TopCat, and you can use various programming languages to actually look at objects. We will not be doing this in detail, but all these are what come under virtual observatory, and virtual observatory is basically all Java-based software. So therefore, irrespective of what is your operating system, you can always use any of these tools with whatever system you have, whether you're using Windows, Linux, or Mac. DS9, TopCat, etc. will work on any operating system. Metadata, like I mentioned earlier, is data description about the data, which I want this thing. Now, all this data, what is available, is sitting in what are called astronomy archives. Okay, this is from where you're going to access the data. So what is an astronomy archive? It's basically organized systematic information about the sky, and you can actually, it could be of variable sizes. The earliest archives were made by Hipparchus, by Tycho Brahe, way much listing. But in today's times, you have much larger listings. This is the Palomar Sky Survey, which is standard used by people. It was observed with the Palomar Observatory, but this is made up of photographic plates which covered the whole sky. And then it was digitized in what is called the DPOS, or the Digital Palomar Sky Survey. And you can access this using various virtual observatory resources. Now, as time evolved, right, that was with photographic plates, people used what are called CCDs. So this is a CCD chip to show you a small chip. It's made up of these pixels or picture elements on which you're going to basically record your data, right? CCDs have a very big advantage over photographic plates for the simple reason is that they're much more sensitive, quantum efficiency. That means most of the photons which fall on them are detected. They have a large dynamic range over which they can observe. They are essentially linear detectors over a large range. So you can actually check up when is which is the range in which your detector is linear, so that you are going to always use it in that kind of range. So we adjust the exposure times when we observe so that it is in the linearity domain. And they have a very good quantum efficiency. So CCDs are what have led to this revolution in astronomy. They are used in other wavelengths also. Technology goes hand in hand. Astronomy archives are in the true spirit of science. The advantage is that these are archives of the best of data you can ever dream of, right? So, for example, even if you want to observe with James Webb Space Telescope, this is the $11 billion telescope on which it's very difficult to get time. There's already data available from James Webb, which is freely available to all, right? So you don't have to write any proposals so that you observe with it. There's already what we call legacy data. There's various sources of data, not just James Webb, but Hubble Space Telescope, or for example, ESA Gaia or Galax. There are many, many telescopes, ground-based as well as space-based, for which all the data is available. So I would say this is the true spirit of science. You have access to the data. You just have to plan your science case as to what are you going to study, and the data is already available. You can download it, do your analysis, and get your science. So there are many various data archives. You people have this PDF, so you can have a look at this. Vizier is a source which actually gives you data of published papers. So you can get this from Vizier. Simbad also gives you data about objects. NED is the NASA Extragalactic Database, which is basically for objects outside the Milky Way. There's the Sloan Digital Sky Survey, the TUMAS survey, the ESO observational this thing. There's a MUST archive, which is at the Space Telescope Science Institute. So that has data of Hubble, James Webb, Kepler, TESS, Galax, various other sources. And there are many much more data archives like that. So this is the Hubble MUST one, which, like I said, has Hubble, it has James Webb, TESS, Kepler, various sources which are there on this site. And you can actually access this, get the data. There is Gaia, which is a European Space Agency satellite, which is gives you right ascension, declination, parallax, radial velocities, proper motion array, proper motion deck to 1 billion stars in our galaxy. Very powerful data source. There's the GMRT, which is the Giant Meter Radio Telescope, which is a radio telescope run in India. You can go to their archival site and you will find all observations from the past which have actually been used, which have used the GMRT. The Chandra X-ray telescope has an excellent website where you can actually access the data archive and get data of all objects which have been observed with Chandra, right? And you will get that data. This is the Sloan Digital Sky Survey, which is most detailed three-dimensional maps of the universe. You can actually use this very effectively. And like I mentioned earlier, the Virtual Observatory is a source which combines the data from all these different multi-wavelength studies. And you actually have data centers where the data is sitting there. You can access them. The data is available in FITS format, or there is also a virtual observatory format. The FITS is for images, but then you can have your data also in, for example, VO table format, etc. So it basically has the data archives, the software providers, and the data centers. There are various virtual observatories all over the world. India has theirs over there, Russia has theirs, and there is also for many more countries, for example, Japan, Australia. This is the German one, the French one, they all exist, and there are 23 such VO projects. And I will end with this, and thank you very much. So now we'll go back to Jupyter Notebooks, and we will look at how do we look at FITS files, which are the image files which you can get from these data sources. Thank you. I'll hand it over to Najam. Oh yeah, and any questions? I can take one or two questions till the time he does things. Are there any questions? Please write it on chat, or we are now going to go on to our Jupyter Notebook on images, right? Okay, thank you. Yeah, you could even put your questions on the Slack channel. Thank you.
Yeah, hello everyone. So having heard the two presentations, I will continue with FITS. So you've been told by Alexei as well as Priya what FITS files are. And I'll show you how to handle FITS files in Jupyter Notebook using Python. So this book will be, Jupyter Notebook will be provided to you along with the required image files in your GitHub page. So now we go into introduction of image analysis and processing. So working with FITS files. FITS, as has been mentioned by both the earlier speakers, FITS stands for Flexible Image Transport System. It's a standard file format used in astronomy for images, spectra, and tables. Like Priya mentioned, these are cubes and with various slices of image of an object in different wavebands, and a cross section, horizontal cross section gives you spectral slices as shown in this figure. So we start off as usual with importing the libraries, and I'm importing here import numpy as np, import matplotlib pyplot as plt, and from Astropy IO import fits because we'll be dealing with fits file. Here I have commented out a few other things, matplotlib, RC parameters, and these are just to improve aesthetics of the plots. But these three which I have on top are the most important ones for the present session, and this is what we shall do. So now I want to open a fits file. It is downloaded where I'm working from, and the name is 1img.fits, right? So this is an image of a galaxy from Coma cluster, and the command used is fits.open, and in parentheses you put name of the file, 1.img.fits, that's the name of the file, and this is in inverted commas, okay? And I'm saving it in a variable called observation. So this is an observational image where I've stored it, and if you run the command obs.info, it will give you the information about this file. So it is showing that file name is this, and then the slice is a 0 primary and 1 primary HDU, 611 cards. The dimension is 501 to 701, and the format is float. So basically, CCD images, you can imagine them to be matrices. These are 2 by 2 arrays where numbers are stored. All CCD images are black and white, but if you take images in different colors, blue, red, and green, or blue and visible, you can construct colored images by combining them. So here we are, so as you know, this fits file, it has one slice which is the primary 0th one. So I can save that in a variable called image underscore obs. Either I have commented here, either you can say image obs equal to obs square bracket primary, or you can call it 0. Yeah, it's given here 0, or the name is primary. You can use the upper line or the lower one to do that. So once I have done that, and if I see image.obs.data, what we notice is it's an array. It's a two-dimensional array with some numbers. This is what it said. The format is floating point. These are real numbers, floating point numbers. So 0.0064, 0.08, so on. So basically, this is a rectangular array of numbers because CCDs are picture elements which collect photons. So if you expose it to any object, at each pixel it collects a number of photons, and those counts are given here. And we can treat it exactly like two matrices are done. if you have two arrays, two matrices of same dimension, number of rows and columns are same, you can add them up, you can subtract them, you can do all kinds of arithmetic operations exactly like it is done with matrices. So we will be using this here to show why it's important. So I have, by saying dot data, I could see the data, and now that you have a two-dimensional array, I will use matplotlib, which you have seen earlier, to plot this image. So plt.implot, if you recall on top, we have said imported matplotlib.pyplot is plt, and here I am using plt.imshow, and the image which I am showing is this data of slice of it, and these are the two CMap, the color maps which we have. I'm using Magma, and I'm also plotting a color bar along with it. So once you execute that, you see this image, and you'll see a small blob sitting somewhere in the center. This is the galaxy which we have. The color map we have used here is Magma. I can change it to any of these gray, or see it's become gray, or I can use um, uh, Verdis or CVD. I can change these color maps, and it is just to see it in different colors. Okay. So plasma is what we have used, maybe because it's giving us, yeah, magma is what I had used, and I'll go back to that. So you can change the color maps and see this thing. Okay. Now, if I want to see a certain region of the thing, the whole plate is pretty big and the galaxy is sitting here. So I realize where it is sitting, and I say Vmin is 0 and Vmax is 0. And I'm plotting the same one, and here I'm just expanding the small blob and seeing this image. Okay. And like said, FITS images have header information too. It's not just the image in different brands, but it comes with other information like the header information. And ims underscore obs header, when I run, I see the header information, which says it's a fixed format. It is bits per pixel. What is it? Origin, yeah, and the date when it was taken, date when it was generated, and all the details are given here. The telescope used was Hubble Space Telescope. Instrument used is this ACS uh, camera, and all the details which are required. What is the target name? It is COMA41, and proposer's name, various things are given. Exposure information, so many, sun angle was so and so, moon angle was and so, sun's altitude. So all these details are given, and these are used for image processing and making images important. It gives you the bias levels and calibration files. So all these, it's right. So this image which we see as a simple one img dot fades, it has along with it, and in header, all this information uh, which says how the image was taken, the exposure time, the observatory taken, and so on and so forth. Okay, so here's something more I would like to show you. There is people who are interested in studying galaxy morphologies. They can use a certain tool called GalFit, and you can fit a galaxy this looks like an elliptical galaxy, so I'll fit an elliptical galaxy on this. I'm not showing how it is done in this lecture, but it has fit, and I see what is the major axis, minor axis, inclination, and so on. And I fit, and I've created a model image which I have with, as one out dot fits. So this is the model image, and I'm storing the primary. Here, instead of using 0, I used in inverted commas primary. We could have said model square bracket um, 0. And if I look at the header information, it tells me the header information that it is a Galfit uh, image. It is created with what search index and certain things. Okay, so the reason why I'm trying to show this is now I can plot this model which I have got, and you see this is the actual observation, and this is the model image, and they look pretty much pretty good. And what I'm going to do in the next cell is I'm going to subtract the image 1. From that, I remove the model. And if it's a good fit, okay, and I'm saving this in the residual ID. Okay, so here I'm saving it here. And when I uh, plot the residual, I'm seeing that it has got rid of the whole of the galaxy. It's leaving almost nothing except for some sources which are in the foreground or the background. If you see, this was the model image, and in this, all these small objects which are around, those have been filtered out, kind of confirming that the image which we have done is a good one, right? So advantage of this kind of subtracting two images or adding two images. Similarly, if you have two images of the same type, you can add them up. See, for example, if you are imaging two objects which are close by, one is very bright and the other one is very faint, and if you give an exposure time only for, say, 10 minutes, you may capture the bright one, but the faint one would disappear. And only if you give a long exposure, say of 15 minutes or 30 minutes, you'll get the other one too. But if you give a 30-minute exposure, then the bright object uh, floods the whole CCD, and it spills over to the other pixels. So what can be done is you can take many small 5 minute exposures and add them up, and it will be equivalent to 1 15-minute exposure. And this avoids uh, um, saturation and other things. So now you can, yeah, so we have seen this. Similarly, you have another image from DSS to IR fits. There's yet another image. So I'm using the same command, fits.open, and I'm uh, storing it in this variable HDU, and I'm seeing what this HDU. It says Astropy input output fits primary object. And similarly, if you run this help command on HDU, it tells you more about that object. And similarly, you can run, uh, you can check the header information. So every header data unit normally has two components. In Astropy, these components are accessed through the two attributes HDU.header and HDU.data, right? It can have others too, but these are the two essential ones. And fits image headers can contain all the important information about the coordinate systems used, and we have seen that earlier, right? A lot of details about the exposure time, who observed it, when was it observed, what camera, and so on. So here when I am looking dot header, I get the header information of this object, and it gives you all the details, and right, in which pass band was it taken, 327 to 422 THZs, and right. So epoch was we are using 2000 RA deck, and all these. So DSS to IR survey. It gives all the information. So the header information comes with a lot of. Similarly, we can look at the data, and you can data is HDU0 dot data. I've mentioned I can write 0 here, or in inverted commas write primary. And the type command is used in Python a lot to see what kind of this variable is, and it is showing that it's a NumPy array, right? As we had seen earlier. So here you have a small exercise to display image. What we have done that with image one. Now you try to do the same thing with this one, and so on. Okay. Coming to the next part, we can do scaling and stretching of functions. And I have, um, I'm using, I have another image which I have here, which is the, um, which we have read it in HDU, right? Which is the Whirlpool galaxy. And it's data, variable data. And when I use numpy.log10, so I'm taking the log of the numbers which are given there, and I'm plotting it. Again, I'm using matplotlib, and I'm putting the title that it is M51, and this is what we are seeing it in the log scale, right? So if we don't take the log scale, then it would have come as the origin one, right? Okay, so you can similarly try out an exercise where you take linear or square root, or yeah, base 10, log 10 was to the base 10. You can change the base to different ones and try it out. Okay. Similarly, there's another exercise. So basically, you have an array of matrix of numbers, floating point numbers, real numbers, and you can do all mathematical computations on that and do it. And you can play around with that and see how you can see the same image in different levels and so on. So coming to the composite image, RGB. So the RGB color models relate to very closely to the perceived colors which we have. And because, right, so if we have images in red, green, and blue filter, you can combine these three images exactly like we did. You can add them up. You have an image in red, you have in green, and you have in blue, and you can add them up and save it in another file, and then you can see the data part of it, and you can plot it using matplotlib. Coming to the Sloan Digital Sky Survey, SDSS, it's a major multi-spectral spectral imaging and spectroscopic redshift survey using a dedicated 2.5-meter wide-angle optical telescope. And the observatory is in Mexico, United States. And they observe in all these wavebands, and I'm looking at the pip install Astroquery. You have done that. Now from astroquery.skyview we import Skyview, and the Skyview lists surveys. If you do, it gives you all the surveys which we have: Chandra, VLT, HST, Spitzer, Herschel, and so on and so forth. Okay, so just a minute. This is yeah. Okay, so with this we will come to the next one. There are some exercises below. Use this RGB to get it in R, normalize it and run it. And these are some codes for you to try it out. And there is a code right in the bottom which shows you how you can save your your file in FITS format. And it is the command HDU write to, dot write to, and give the name of the whatever file and overwrite. If you say overwrite true, then if that file already exists, it overwrites it. Otherwise, it will not do it again. So, for example, we have done the same thing above with the residual image. When I subtracted the model from this, I had have fits.write to here. If I don't have overwrite here, and if I try to run this again, you will notice that it will give me an error because already this res.1.fits is sitting there, right? So hence you have to write if you want to overwrite it. This is just a mechanism so that you don't by mistake overwrite what you have done. You can run the same thing with some other name, then it would be fine. In case you are doing some other computations and running it. So I will, for example, when I'm writing it here, write to, if I change the name to say 2 and run it, it would have run and it would have created yet another file. So with this, we'll come to the next Jupyter notebook, which is also being shared with you. And Priya, you want to do that? This is how you can access. Priya spoke. Priya has spoken about the various surveys and data centers and from where you can get the data. And we'll use Python notebook to show how you can get it from a URL. You can get it from the site. What we have here is the file sitting right in your where your Jupyter notebook is, or you specify the path where it is sitting. But now we will see how it can do it from the net. Okay, over to you, Priya.
Yeah. Yeah. So thank you. And now we are going to have a look at basically how can you access data, astronomy data, what I spoke to you about the archival data, etc. How do we actually access it from the using a Jupyter notebook? Now, obviously, these things can be accessed not only through Jupyter notebooks, but through other ways also. This is one of the ways. Sorry, I'm just sorry. In which you can actually access it. Okay, so I hope you can see my screen here. Yeah, it's good. Okay, so what are we going to do? So there is something called the CDS, which is a Center for Data in Strasbourg. This is in France, okay? And this basically houses the data, for example, the Vizier data, Aladdin, there are various other sources which are run by this thing. Okay, so you can have a look at all this, and I'll run some basic, you need to use Astroquery, right? You was spoken about Astroquery. This is in Astropy, okay, which is actually used to query astronomy data. Like the name itself suggests what it actually means. So that's Astroquery. So the notebook is present with you all. It's there on the GitHub page. It's called astrodata.ipynb. So you can download the notebook and upload it in Colab, and we will run it together so that you can see what are the things which we are doing in this. So like I said, first we do that. Then there's something called IP Aladdin, right? IP Aladdin, which is basically a Python-based this thing. Now, you can even write MockPy, we may not use it, okay? So as you come down to the, as you come down in the notebook, you will see that there is a part where you're actually using Aladdin. Aladdin is basically a virtual observatory tool used to display data, okay? So for example, if you look at this over here, This is Aladdin. I'm picking up a survey, which is basically the decap survey, okay? And I'm looking at the galactic center, okay, with a field of view, 40 degrees and a height of this thing. So I run this command, and when you run this command, oh, okay, sorry, I'll just run this. I didn't run IPy Aladdin, import Aladdin, and then you come here. So when you see over here, you will actually see that this is interactive, okay? So you can actually see that if you move your mouse, right, you can actually zoom in and zoom out at this source, okay? So Aladdin can be separately, like I told you, these are Java-based softwares. So you can actually Google Aladdin and find it on the net and download it as a Java-based software, which, like I told you, it will install irrespective of your operating system, right? So it will run on Windows, Linux, Mac, everything, and you can download it. Otherwise, the other option is you can also access it through a notebook. So here we are accessing it through a notebook, so you can get this. So once you get this, you can actually save the data file in FITS format and get it like that, right? Now you're already familiar with using Astropy coordinates. So from Astropy coordinates, you may actually import angle this thing. I may put another target. Here I'm putting another target called antennae. Antennae is a galaxy. It's a set of interacting galaxies. So if I actually run this, I can actually use the antennae galaxy in Aladdin. You can see you can't see it. Therefore, I'm going to move this and I'm going to zoom it. And if you zoom it, you should actually get the galaxy sitting over here, right? So this is a very interesting thing where you can actually interact with this thing. You see, you can pan it, okay? You can move the panel you are getting, and as you're moving the panel, you will see that this, as you zoom in and out, you can see your field of view. This is the field of view of the sources you are looking at, okay? On top, you can see the array dex of the source. You can actually stat up different overlays on top of this, right? You can overlay it with some other data and put some overlays of some other catalog. For example, over this, I can overlay, for example, the 2MAS catalog, okay? So my 2MAS catalog is getting loaded onto this data set, right? Onto this image. So I can actually add various overlays. So you see now I can see my 2MAS sources, which are marked onto this thing. I can add another overlay. For example, I can take it from some survey or I can take it from a catalog. For example, I take Gaia DR3. I may even add this onto this. So now you can see over here, Gaia DR3 is being added on. Exactly similar things can be done if you're using the Java-based software of Aladdin. Instead, old timers like me, who belong to the times when this did not exist, we are still much more comfortable with the standalone, with the Aladdin which you install on your system, right? I somehow feel that has much more flexibility than the Jupyter Notebook. But agreed, there could be times where you may want to put it as part of your Jupyter Notebook, so you may use it in this. But old timers like me, I'm happier to actually download the Aladdin software and run it on my system. But it's just a matter of choice. So here you can see the blue squares are the Gaia DR3 sources, while the red plus signs are the 2MAS sources. So in short, I get all my sources like this. I can actually install all these things, right? So this is how I showed you to start Aladdin Lite, okay? So this is the Aladdin Lite one. If you use the one on your system, you will have even more capabilities. So using that, what happens is you can actually look at a source, you can overlay your catalogs, whatever data you have, and look at it. I also told you about Vizier. Vizier is basically a set of data which is basically which is from published papers, okay? So supposing somebody publishes a paper about some objects, right? Then he or she can upload the data onto Vizier, okay? And from Vizier, you can directly download the data of a published paper, right? It could also be even catalogs, for example, 2MAS catalog or Gaia catalogs, etc. You can download it from Vizier. So one way of doing Vizier is you can actually look at this. I'm just showing this to you. I can actually just Google Vizier, for example. Sorry. I can just Google Vizier, right? and it will actually take me to the Vizier page. Okay, and this is the website. I can directly access, this is website, which is with the CDS data center, and I can actually, it's taking a little time to load, but it says there's no catalog, so I put your thing, and you can see over here, if you use the browser, you can actually access. For example, supposing I want infrared data, I can actually choose which mission I want. For example, I want infrared data from, for example, WISE, okay? And I'm looking at, for example, AGN, right? So I may actually find catalogs which are there using infrared data with this thing, but there isn't anything over here. So let me instead take, for example, this is WISE data. Let me take clusters of galaxies, look for catalogs, right? Or I will just, let me just take it. So you can actually use this, supposing you, this is the 2-mass catalog. So then I may actually look for this. And here you can get the 2-mass catalog. I'm sorry. Let me get some other thing. Yeah. I think this is creating a problem because I've selected these missions. I should have not selected the missions. But you can actually look for catalogs and look for objects with this. But what we are instead going to do in this today is I'm going to access it using this Jupyter Notebook. So here there's a catalog by ARP. Okay, so I'm saying catalog list. I'm going to find catalogs written by ARP exactly in the same way for this thing. So ARP, basically I'm running this, and ARP basically has 2 catalogs. There is one catalog of peculiar galaxies, which is this one, and then there is this other one, ARP's peculiar galaxies. So what I do is I decide to, for example, there is what is called a TAP service, which is the Table Access Protocol, which is part of the VO. So what I can do is I can do this, and I'm actually using the TAP service to take where tables have the name ARP. And here you can see these are all the tables which have the wildcard or the name ARP. So you can see here are the various tables which are mentioned over here. Okay. And using this, I can actually choose which table I'm interested in. Let's say I'm interested in this one, which is the 192 one, right? You can see it is 192. So where is that? So I want to look at this one, which is the ARP list for involved galaxies. Basically, involved means interacting galaxies. So I want this thing. So I'm looking at this thing. It's ARP's peculiar galaxies. So then what do I do is if you write Vizier row limit -1, it basically takes in the whole catalog. That means the row limit becomes infinite. Okay. So how many ever sources are there? I may say Vizier row limit -1, and I take this from this catalog. And now here I can print my catalog. So now you can see I've printed the catalog, and here I've now saved it as table ARP list, and here is my table ARP list, which is my list of ARP catalogs. So here is the ARP galaxy number and other details about the galaxies, right? I may use it even to get some other data. For example, here again, I'm querying this. You have these objects, and I may actually add table and put it like this, okay? So I may get that data source in that way and do it like this. I may also try to cross-match these galaxies, for example, with SDSS galaxies. So I say info asset, find data sets, metadata this, and I actually look for all the SDSS galaxies. And then what I do is here you can see this is my galaxy ID, I'm matching it with that, and I can actually use this to, match those ARP galaxies with the SDSS galaxies, okay? I'm going to now talk a little bit more about home ground because I deal more with Gaia data. So for example, here I'm going to show you how would you access Gaia data, okay, if you want. So again, these are the basic libraries which are used, okay? Seaborn is for plotting, and I may take these galaxies. So therefore what happens is, again, there is a website with which you can access the Gaia data, okay? So for example, you can look over here. This is the ESA Gaia data archive. If you go into this thing, I go here and I can Yeah. I may go to the Gaia data. This is available online, and I may actually. I'm sorry, it's taking a minute to load. Right. So you can actually see that here you can go in for search, and when I search, I can search for an object. For example, I can search for M45. It's getting resolved by this thing. I can actually put my object, say look within 5 arc minutes, and I can put in my query, right? I can put in a query and say submit query. Okay, this is how you do it from the browser itself, right? Otherwise, what we are going to do today is, if I have a Jupyter notebook. In a Jupyter notebook, I'm going into the same site. I log in as anonymous, okay? Otherwise, in principle over here, you can go in and you can actually log in, right? So I'll show you this thing where you can sign in, right? You can sign in. I basically sign in because I'm a regular user of Gaia, and I'll sign in. But otherwise, you can, in this notebook, I've just kept you as an anonymous user. You say login is false and you say this thing, okay? Now, for example, I'm looking for this object 1960. I find the sky coordinates from the name. So that gives me, over here, you can see I'm printing the array and deck of this source, which is NGC 1960. Now what do is I actually look for a radius around it, which is half a degree. So you can see 0.5 into, this is units degree, right? If I would use it in, I could use it in degrees or in arc minutes or in arc seconds. But here I've taken U as U dot degree. So 0.5 U dot degree. The maximum magnitude I'm saying is 18th magnitude. That means I want stars only which are brighter than 18th magnitude. Typically Gaia has magnitudes up to 21. But obviously, if you go in for fainter magnitudes, the errors in your data is higher. So basically, we are trying to ensure that we're getting high quality data by doing this. Now, if you, the earlier website I showed you was this, where you could actually do your query using the website which I showed you, right? But otherwise, in astronomy, there also exists an astronomy data query language, right? And this is called the ADQL, which is something similar to MySQL. So here you can see in this query, this is MySQL data with which you can actually use this to access the data. The other option is, like I showed you earlier, for example, this one, I'm querying it to get the brightest 1,000 stars, okay, which are in the certain, in which are close to us. Parallax is greater than 10. So in Gaia, the parallax is basically in milliarc seconds. So distance is 1 upon parallax, so it becomes 1 upon 10, but 10 is multiplied by 10 power minus 3. Right? And therefore it actually becomes 1,000 divided by 10, which is 100. That means here we are basically looking at all the stars, the brightest stars, which are within 100 parsecs. Okay, so if I run this over here, I'm running this query, it's getting me the brightest stars with a distance of 100 parsecs. Here are my brightest stars, and I can actually save the result into a file called gaia.fits, either in FITS format, or I can put it in CSV. CSV is comma separated variable, so I can run it like this and I can get this. So if you're in Colab, when you run this over here, you will get these two files, right? This is your gaia.csv, gaia.fits, and I can actually right click this and I can download the file, okay, which is generated. Please remember, whenever you're using Google Colab, everything is on the fly. So therefore you need to save it if you have got to save it. The other way is I can actually run in a Jupyter notebook to access the same archive which I just showed you on the browser. So I'm loading the Gaia archive through, this is exactly like I was using Aladdin Lite to access Aladdin. Similarly, I can use this notebook to access the very same site which I just showed you 2 minutes ago from my browser. Again, over here, I can search it, right? And from here, I can get this object, which is, for example, M45, right? And I can query it at an area of this thing. I can say submit this thing. I can also say show query in ADQL format, or I can even say save it in whatever format I want. That was available on that page too. And I can save my data, right? I can also do something. Here I already have it saved. So I'm going to actually upload this thing. I have this sitting on my m45all.csv. So I upload this onto my Google Colab. Okay, so you can see here I'm actually making a pandas data frame of my CSV file, which I'm calling all stars. So here are all the stars which are in this cluster called M45. Okay. Now, if I can plot the sky plot. I'm sorry, I'm running through this thing because we are running a little bit out of time. But I hope you all are understanding the syntax. This is using Seaborn. Seaborn is basically being used to plot array decks of these objects. If you see here, I have array and deck. You have to be careful to take the name of the column as it is in the data frame. And here is the plot of these things. But I have all these stars in this area and I do not know which ones are members of the cluster, right? So how do I find that out? What I do is if I actually plot an HR diagram of these stars, I will get a plot like this because my X in Gaia, you basically have G magnitude and then you have a BP, which is the blue the magnitude, and RP, which is the red. So typically when we do an HR diagram, the y-axis has one magnitude and the x-axis has what is called the color. That means a difference of brightness in two filters. So I'm taking BP minus RP and these are all my stars. But I do not know which are the stars which belong to the cluster. So now what I do is I do a simple plot over here. I'm going to do a histogram plot of the parallax. So if stars belong to a cluster, they should all be at the same distance. That means they should all have the same parallax. So when I'm looking at all these stars, this is the distribution of parallax. You can see that there's one distribution which is centered kind of around 0. And there's another distribution which is centered around something like 7, 8, something like that, right? So the cluster stars are not these stars which are centered around 0. Because these are all the random stars. You'll have some of them foreground, some of them background, so they'll be centered around 0. But you'll have all the stars sitting over here. So I know that the parallax lies somewhere between, say, 6 and 8. Okay, this value. Similarly here, I'm going to plot the PM, RA, PM deck. Again, all the stars in a cluster move together, hence they should have the same velocities. But you can see that this group is centered around 0, 0. But there's another group which is centered somewhere around something like this, minus 45, 20 and minus 45. These are not the cluster stars because these are the background stars which are moving away and towards you. But these are all the stars which are moving towards. So these are our stars of interest and not these. So now I basically know what is my range for cluster members. For parallax, it's something between 6 and 8. And for proper motions, RA is something like 20 and deck is somewhere like minus 45. And therefore here I define a mask. Okay, a mask is the region which I'm identifying are the members. So I'm saying my mask is parallax greater than 6 up to 8.5. Proper motion RA, you can see it's centered around 20, but I'm going to basically taking between 10 and 30. Okay, greater than 10, lesser than 30. Similarly, PM deck, which is somewhere like 45, I'm going to take it ranging between all stars between minus 40 and minus 50, all these stars. So I'm taking this range and I'm identifying the members. So I run the mask. I say members are all stars which are from the mask. So now when I run this, I plot now my HR diagram for number one for all the stars, as well as you see here it's for all stars and here it's for members. So all stars are in blue and my members are in orange. So here I have what is called a clean HR diagram, which is the HR diagram only of the member stars. So here we've used Gaia data to effectively find out all the members of M45. Okay, so I will stop somewhere over here and I would be happy to take questions now. Yeah, so a similar capstone project would be about, say, studying membership of stars in a cluster. Once you get the membership, then you may study other properties of those stars. For example, their initial mass function, their mass distribution, or various other parameters about those stars, right? So I'd be happy to take questions. I hope you all know where all the recordings are. Look for Bricks Astro on YouTube, you'll actually find it. Yeah, so Zifar Raya is asking me see, all this stuff is sitting on your GitHub page. I'll just show you where your GitHub page is. If you go for GitHub, yeah, this is the Bricks Astro the GitHub repo. And here you have week 1, week 2, week 3. Today is week 4. So here is your week 4 files. This is the talk I gave you earlier was Astrodata, which is sitting in this PDF file, while the notebooks which Alexei showed you are these 3 notebooks. 1 to, okay, now it's actually 5 notebooks. You have 1 to 5. These are all Alexei's notebooks. And
We'll replace.
where are my
No,
notebooks? Okay.
Priya, 5, 4, and 5, it's your notebooks. The Astro CDS and image analysis are your
Okay,
notebooks.
sorry. Okay, so Daniel has renamed it. So this one is, yeah, 4 and 5. 5 is what Hassan sir showed you, image analysis. What I showed you was this one. And 1, 2, 3 are all Daniel, right? The data file is sitting over here, m45.csv.
And then if you go to supplements at the top, the folder,
yeah,
yeah, we do have a notebooks, additional notebooks for different kind of query
okay, wow.
examples.
Oh, beautiful,
Yeah.
very nice.
Yes,
Very
so
nice.
there are tons of, even people can get ideas there for their project. For
Yes,
example,
okay.
SDSS NR SNR plot.py. If you click on it, let's see.
Yeah,
Yeah.
yeah.
Yeah, it shows how to read an
Yeah,
SDSS.
download spectral data from SDSS. Okay,
Yes,
wow.
and then how to extract the spectra.
Oh, beautiful. Very
Yeah.
nice.
So yeah, this is their plotting the spectra and all
Okay.
that. So there are a couple of examples there. We added data supplement for people to check out. One is on manga. So a couple of them, they are all great
The manga
examples
one.
for,
Which
yeah.
is the manga one?
Yeah, so
Yeah. Yeah,
yeah, go
so
ahead, Frida.
yeah, no. So, for example, what you just saw the notebook, this was of analysis of SDSS spectra, right? So, typically, if you want to do a capstone project, for example, SDSS, it's basically galaxy spectra. So, you decide a certain galaxy sample, right? So, define your sample, whether you're looking at AGN or you're looking at spiral galaxies or you're looking at a certain kind of galaxies. So, once you define that, you can actually use SDSS to download spectra of a whole sample of galaxies and then look for properties in the spectra of those galaxies, right? So that could be some kind of a capstone project which you can do with galaxies, right, using SDSS spectra. Or for example, like what you have these other ones, you have a data cube, for example. You can, I spoke to you all what are data cubes. So you may actually, yeah, this is for manga observations. So you may actually use manga, Google it, you look for manga observations. Here you have the thing and you can actually calculate the errors and, look. So you can look, I define a galaxy sample for which you're doing this. What is closer to my heart is stars. So for example, if you're using Gaia, you can use Gaia data to also study stars or star clusters or various properties of stars. From the Gaia data, you can use, you already know what is SDSS, there's manga. And, have a look at all these. What is Galaxy Gaussian? For example, how to create a Gaussian model of a 2D galaxy. You can have a look at this. And you have, yeah. So very good. This is nice. Okay. So please have a look at these and, ask us questions for whatever you find interesting.
Yeah, and then
Similarly, if you're looking at
okay.
if
Then
you're
Najim, go
looking
ahead.
at clusters of galaxies, you take from HST, in one frame you will get many galaxies. And if you want to cut out certain stamp posts of certain galaxy, then you can do that using Python. Exactly like we saw there. You specify the X limit, Y limit, left and right, and from mosaic or a picture where there may be many objects, you can pick up one portion of the frame and
I'm
analyze it.
sorry, Priya, can you mute your mic so that it wouldn't echo? Yeah, Najim, you can.
Yeah, can you hear me?
Yeah, it's better now.
Yeah. So what I was saying is exactly as we have seen what these images are, PITs, CCD images, they are arrays. And if you have an image where there are many objects, you can cut out portions of it, specifically one specific object, by taking the x left limit, right limit, and y limits, and you can just cut out those portions and do analysis, plotting of photometric profiles or various things in Jupyter notebooks. So the whole thing is a big ocean, and what we are doing is just introducing you all to the fundamentals of it so that you know what are the possibilities which are there, and you have to build on that. And there's a big community out there, available on the net. They are ready to help and troubleshoot your issues. So, yeah, so use the resources which are available on the net to define your problem, access the data as the way we have shown, and analyze it to make science cases out of it. Okay.
All
Any
right, thank you
questions?
very much, Najem. Let me see if there's further questions. Yeah, so each participant should get on their project. So let me share my screen for the last time. Okay, and I haven't shared my screen today. Yeah, apologies, I still don't. Yeah, so this is the link for the GitHub project capstone. I've shared it in the chat. Let me zoom this so you can see properly. Okay, so we're looking at the basic criteria as you choosing your project topic. And again, because we also know that maybe there are people who are not so conversant with astronomy that are taking this course because they want to learn the data analytics and Python part. So if you're not convenient with astronomy, you can also choose other domain. Maybe health, climate, business, economics, anything you think you like. And then, but we expect you to choose a topic that is quite relevant for the BRICS contest. Maybe it can be a data related within the BRICS ecosystem, in any of the other field. Or if you can't, you can also work on any data of your choice. So we expect that you should submit your output as a Jupyter notebook, but the notebook must be in Colab. So you can work on your PC. Then after working on your PC, if you have a good PC, you can put the code in a Colab, make sure it has a link that is shareable. And in that case, because we are trying to automate the process of submission, and we don't want you submitting notebook files and then we'll keep downloading it one after the other, trying to open it and running it. So we want a case whereby when it's being graded, you just click it, it opens up in Colab, and then we can see your results. So make sure you write your text. If you want to add an image, you can do that as well. You can Google all of those shortcuts, Jupyter Notebook shortcuts. So you need to write a description, title and objective, the title of your project, the objective, what you want to achieve, describe the data set, where you got the data, and if possibly provide a link to the data set. Then we expect you to perform basic data cleaning and doing data analysis. And then if you think you can model, you have mentioned, because we're in 2 weeks time, we'll be talking about machine learning. If you think it's something that you want to try out with machine learning, that will be fine. But if you can't do so, please, you can also use basic data analysis skills that you've learned over the last 2 weeks to apply to the data set, make beautiful plots that is explainable. And then we also want you to tell us what you have learned from this analysis. What insight have you generated and how is it relevant? You understand? Because the idea of looking at data is that we want you to be able to go through the process of collecting data, performing the cleaning, analyzing the data, and generating useful results. For example, barely looking at what Priya shared a moment ago, in her Jupyter notebook. She went from collecting data from Vizia, Gaia Archive, and went into doing some basic analysis in terms of making plots, saving the data, taking a sample of that data, and now making a column magnitude plot that you saw in her presentation. She also showed the coordinates, the positions of in the sky where those stars, Gaia sources belong to. So these are some of the things that we expect you to do, but not only in astronomy, you can also choose to do other use cases, find other use cases. Again, it is important that you add references. So if you've used someone's data, you need to also add reference. If you've collected data from somewhere, you need to also make sure you provide a link to where you collected your data. And this is week 4, remember? So we're expecting that you should be working on this. You have roughly 3 weeks more. You have 3 weeks more to complete this project. So take your time to search for data. You can interact within the Slack community, in the Slack group, to ask questions if you're confused on how to go about it. A link has been provided for where you can possibly get data. But this is not exhaustive. This is just for you to try out. So these are the ones for astronomy. EXA Archive is the one that Priya just shared with you. If you are not so comfortable with using Python yet, you can also go and go to the link and not just you can inspect, get your hands dirty, look at it, look at the interface. But she already provided a code on how to query the same Gaia archive data. We have a link to NASA Exoplanet Archive, where you can check a whole lot of exoplanet data sets and download ones that you think are relevant for you. Then we also have a link to the Astroquery. The Astroquery link is basically what Priya just demonstrated in her notebook. So you can, that resource, most of the information that you need for the astronomy section have been provided in the notebooks that is shared with you today. So please go through it. You can also go to the Vizia. If you are confused about maybe getting data, I've also provided a link to Vizia. This link will automatically take you to the Vizia interface. And then on going to the Vizia interface here, you will see this is Vizia. This is how it looks. You can, maybe if you're interested in any kind of data, you can search. A good way to sometimes search is if you're new to this, is just maybe looking at these are different instruments, and then these are different wave bands. So if you're interested in radio data, you can come here and click radio data, and then it shows you you've selected this, and then you can maybe if you're looking at anything like say AGM, then you can do find catalogs. And then here it pops up series of, these are a series of catalogs. Some of them are old, some of them are new. So you just have to keep looking at the headings and see anyone that interests you. And then you can start from there. Let's say this one says Iraq identifications of 400 and 510 Aegis radio sources. If you come here and click this, it will take you to the columns. These are the columns of this data. And if you want to read more about the publication, you come here, there's a link, this takes you to the paper itself. This is the README page. And then you can come to the table here and download the data set. This is the columns here. But you have to make sure you understand what you need to do. You can also read the paper. But then if you're not so, it depends on your level in astronomy. So if you're already grounded, you know some basic things, you know some things that interest you, you can easily go find it. Otherwise, you can also stick with maybe using the very simple ones like Gaia, 2Mass, and the rest of them. And then here we have other open data sets. Number one of them is Kaggle data set. So some of you may have heard about Kaggle. Kaggle is a machine learning, a data science resource for online resource for people who are interested in data science and machine learning, where you can have tons of data sets. You can also find notebooks, a series of examples. So there are tons of resources here that can take you from beginner to novice, that can take you from novice to expert in either data science, data analytics, or machine learning. So they have tons of data sets. You can search, say, maybe something on health. If you search health, you're going to see a whole lot of health data. This is mental health. some student mental health. Some of you are students, so you might also want to, try them out. In cases like this, if you click the link, it shows you the data card, information about the data, and then the size of the data. This is about 7 or so kilobytes. So the data is not huge, but it's something that one can also use to do basic analysis. So there are tons of data. Some of them are also very large. So be careful. And when you are selecting data, make sure you can select data that you can work with on your PC, unless you have a very strong machine that can process large data sets. So be careful and mindful of the kind of data that you have. And yeah, so you can get so many ideas. And some of these things, you will see a couple of examples, even where people have provided their own codes that they did trying to, but please don't just copy and paste. The idea is for you to come and see what other people are doing and learn from there. Different idea in analytics. So you will always see this. So for example, this is somebody doing analysis on healthcare insurance data analysis. So you can see how they're able to go from to checking if there are null values and the rest of them, outliers. These are things that Priya and Najam have taught you last week, visualizations, different kind of stuff. And so this is what kind of thing that we expect you to do in the course of this. So you can explore Kaggle for data sets. Like I said, there are tons of data there. You can also, there's this one, World Bank Open Data. We have Google Dataset Search. We have UCI Machine Learning Repository. There are also other tons of data. So I didn't mention a couple of them here. Even Hugging Face. Some of you may have heard of Hugging Face. So Hugging Face has its own set of data, but let's not go. So if you know how to navigate through that, you can also go and download data there. These are the rules for grading. We will look at, this is how your notebook will be graded. So you have this information, then please go through this, explore it, and at the end of the day, make your notebook. So everything will be in a notebook. So you can, barely looking at this, you can see how this person, this is just a typical example. You can find a couple of something like this in the Kaggle. Though this is not detailed here, this is not fully what we want. This is just a snippet because it's not complete. We need to also write some text to describe what you are doing. At least he gave heading loading data. So things like data description is not there, but you need to also write something about the data that you're exploring and the justification. But I think this is enough explanation so far. So submissions, we expect you to get your notebooks, your Colab notebooks ready. So the Colab notebook is just similar thing as you're doing, so that we've been working with. You can choose to, if you go to your Google account, you can create a new fresh notebook and start preparing that notebook. And the essence of it is that at the end of the day, okay, say for example, let me do this. Let me try Colab. Okay, so let me say a new notebook. Yeah, this is taking a lot of time. Don't know why. Maybe my internet. Okay, so what you can do is here you give it a heading. You can give it any name that you want, something like your name underscore bricks astronomy underscore capstone. And then you can use these two buttons here, text and code. So for example, text means you can write, you can use hashtag to make heading and all that. I think we've explained this, and then you can write something. Yeah, and then you can write your code here and all that. So as you are doing this incrementally, you keep preparing your notebook. This is not going to wipe out. This will always be there because you are doing it it's sitting on your drive. So it's not going to vanish. Yeah, it's sitting on your drive. So you can start from your data description and linking data. So if you're using something like Astroquery query, you can write your code and point it to the catalog. It prints the text, you load the catalog, and then you start doing your analysis. Even if you finish, you shut down. You can choose to shut down the notebook and come back later and continue. It's not going to vanish because the notebook is sitting on your drive. And when you're done to share it, it's going to ask you for share. And then this is when you want to submit. What you can do is you can choose to restrict it to, just anyone with the link. I think that's enough. And then with the link, you can copy the link. If you copy the link, and then this link is what you expect you to submit to us at the end of when we start when we start the collection for this project. So I think we've made it very simple, but in case you have any issue or any problem or challenge, please do not hesitate to reach out or ask questions in Slack. But please, this link is here. If you want to see this link, just come to the GitHub repo, go up to Cap a project and go to Capstone, and then you will find it. You will find it here. Every information is here for you. Please go through it. This is how you demonstrate proof that we have not been wasting our time for the last 5 weeks. I think that's all for today. I'm not sure if there are other questions. Yeah. Okay, I think we are a bit over time. So thanks to Priya, thanks to Naja, thanks to Alexi for providing the resource and engaging us today with the topic. Thanks everyone for joining. Okay, at what address do we need to submit the project? Yes, we'll provide the link towards the end of the program. We're going to provide a link for you to submit your project, your capstone project. Just work on it first. Okay, guys, you all should have a nice day. We'll reconvene here in the evening. Alexei, Priya, and Najam will take us the same thing for those. This is for people in the western part of the world. Remember, we run 2 sections, morning and evening. It's going to also be the same topic. So for those who have joined this morning, there wouldn't be any need for you to join again in the evening. But one thing I'm going to emphasize is that you need to make sure you go through the notebooks and practice them. Read the text and practice the notebook, and also get your hands dirty. Choose to also change things while you are running it. That is the only way you are going to learn. So on this note, have a nice day. Bye, everyone.
Goodbye.
Goodbye. Goodbye. Goodbye.